Imagine you're going for a walk on a beautiful day. You thought of taking a photo of a cherry blossom. When you took your phone out, you realized that the battery was dead. Anyway, you continue your walk. Unfortunately, you trip and fall down. The artificial tooth you have breaks. A spacecraft which was entering the Earth's atmosphere exploded and fell in front of you. Not a very good day. So, let's start the walk again with a few changes. First, we introduce ultra-thin hafnia layers in the sole of your shoes. Due to the nonlinear elastic behavior, every time your foot hits the ground, the hafnia layer flexes and generates a charge. This is known as the piezoelectric effect, and this electricity can be used to charge your phone. Since you have a biocompatible and corrosion-resistant zirconia tooth implant, your tooth does not break even though you fall down, because nonlinear elastic property of zirconia can absorb shocks without cracking. That spacecraft safely landed to its destination thanks to the many desirable properties of hafnia or zirconia coating, most importantly, the nonlinear elastic property which contributes to shock absorption. And you continue your walk. Hello, I'm Ruvini, and I'm working at Professor Bongiano's lab in College of Staten Island. The topic category I'm applying to is cross-cutting computational research. Let's see how we computationally test the nonlinear elastic properties of hafnia and zirconia. Think about a piece of elastic that is being stretched. The relationship between the pressure applied and the elongation will be linear for a small elongations. After that, the elongation is not linear. This is nonlinear elastic region. In both these regions, when we remove the pressure applied, the material is going back to its original shape along the same path. There is no permanent deformation. Hafnia and zirconia reaches this nonlinear elastic region with less pressure applied. What is more important is how they behave in this nonlinear elastic region. When you stretch an elastic, you need to apply less force in the beginning and it gets harder after a while. That means it gets stiffer. In the case of hafnia and zirconia, they get softer when more pressure is applied. The main reason for this is the special way their tiny building blocks called monoclinic unit cells are arranged. This allows atoms to rearrange easily under pressure. Remember Sir Thomas Edison? Even after 10,000 mistakes, the material which was discovered for the filament bulb was not the ideal material. While appreciating their hard work, what if we could reduce those mistakes and shorten the years of trial and error to just months? Thanks to computational simulations, we can now test thousands of conditions in a virtual environment. An apple falling can be described by the equation F equals to ma. In a virtual environment, it would need to move like this following the equation. But we work with crystalline materials. Their behavior is governed by a more complex equation, Schrodinger's equation. With this, we can simulate how crystalline materials respond to strain, pressure, and temperature. Accurately modeling how atoms rearrange under these conditions is challenging and requires highly sophisticated calculations. For hafnia and zirconia, the effects of different conditions have not been studied broadly. Our effort is to figure out the strain, pressure, and temperature conditions that bring out the desirable nonlinear elastic properties for different applications. Thank you very much for your time.